At the center of our galaxy, 26,000 light-years from Earth, there exists something so heavy it equals 4 million suns combined. It's a supermassive black hole called Sagittarius A star. It's so big that our entire solar system would fit inside it several times over. Entire stars orbit around this invisible giant like planets around the sun, only thousands of times faster. Some stars reach speeds of 8,000 kilometers per second when they pass close to it. For decades, scientists could only imagine it was there, observing how stars moved strangely in that region. But in 2022, we finally managed to take the first real photo of this cosmic monster. And what we discovered changed everything we thought about black holes. Sagittarius A star isn't just a cosmic destroyer sucking everything around it. In fact, it might be responsible for keeping our entire galaxy united and organized. How can something that devours light and matter at the same time be what keeps billions of stars dancing in harmony around it? Subscribe to the channel, leave your like, and comment from what part of the world you're watching. Get comfortable and relax. Let's begin. Tonight, we're embarking on a gentle voyage to the heart of our cosmic home, to a place so extraordinary that it challenges everything we thought we knew about the universe. At the very center of our Milky Way galaxy, 26,000 light-years from the small blue planet we call home, there lurks something magnificent and terrifying in equal measure. It's a cosmic giant so massive that it contains the equivalent of 4 million of our suns. Yet it remains completely invisible to the naked eye. This is Sagittarius A star, and it's about to take us on a journey into the very nature of space, time, and gravity itself. Before we drift into this cosmic mystery together, I'd love it if you could give this video a like, and perhaps subscribe if you haven't already. It really helps this sleepy little channel reach other curious souls scattered across our planet. I'd also love to know where you're watching from tonight. Are you settling in from a cozy bedroom in Toronto as the snow falls gently outside? Perhaps you're listening from a warm apartment in São Paulo while the city hums quietly in the distance. Or maybe you're drifting off on a comfortable couch in Auckland as the morning light begins to peek through your curtains. Let me know in the comments. There's something wonderfully comforting about knowing we're all connected by our shared curiosity about the cosmos, no matter what corner of Earth we call home. Now, settle in, get comfortable. You don't need to remember every detail or take mental notes. Just let the words wash over you like starlight. As we begin this gentle exploration of the monster at our galaxy's heart, remember that this video is for educational and relaxation purposes only, and is not intended as medical advice or a substitute for professional treatment. Ready? Let's begin our journey to the center of everything. Imagine, if you will, that our entire galaxy is like a vast city at night, viewed from an airplane window. Billions of stars twinkle like streetlights, arranged in elegant spiral arms that curve through the darkness. From our perspective on Earth, we're like residents living in the suburbs of this cosmic metropolis, looking toward the bright downtown core where all the lights cluster together most densely. But unlike any earthly city, at the very heart of our galactic downtown, there's something that emits no light at all, yet commands the attention of every single star around it. For the longest time, astronomers could only guess at what lay hidden in that bright, crowded center of our galaxy. Thick clouds of dust and gas block our view of the galactic core, like trying to peer through a heavy fog. But just as you might hear the rumble of traffic, even when you can't see the highway, scientists began to notice something extraordinary happening in that region. Stars were moving in ways that didn't make sense, unless something incredibly massive was pulling on them with tremendous gravitational force. Picture a group of dancers waltzing around an invisible partner. You can't see who they're dancing with, but you can tell from their movements that someone or something is definitely there, leading the dance with authority and grace. That's exactly what astronomers saw when they turned their most powerful telescopes toward the center of our galaxy. Stars were orbiting in tight, precise paths around what appeared to be absolutely nothing at all. These weren't just any ordinary stars either. Some of them were racing around at speeds that would make your head spin. We're talking about velocities of 8,000 kilometers per second when they swing closest to whatever was commanding their orbital dance. To put that in perspective, imagine traveling from New York to Los Angeles in about half a second. These stellar speed demons were moving so fast that only something with enormous gravitational pull could keep them in orbit rather than flinging them out into the cosmic void. The mystery deepened as technology improved. Radio telescopes, which can peer through the dusty veils that block visible light, began to pick up intense radiation coming from the galactic center. There was definitely something there, something that was heating up the surrounding gas and causing it to glow with energy. But it was compact, far too small to be a cluster of normal stars, yet far too massive to be anything conventional astronomy had encountered before. Then came one of the most remarkable detective stories in the history of science. Starting in the 1990s, two teams of astronomers, one led by Andrea Ghez in the United States and another by Reinhard Genzel in Germany, began a patient, decades-long campaign to track individual stars as they orbited the galactic center. Night after night, year after year, they photographed the same patch of sky, building up a time-lapse movie of stellar motion that would eventually revolutionize our understanding of the cosmos. What they discovered was breathtaking. They were watching stars complete, full orbits around an invisible object in just 16 years. One star, designated S2, swings so close to this hidden giant that at its nearest approach, it's traveling at more than 7,600 kilometers per second, or about 2.5% the speed of light. The gravitational forces involved were so intense that the star's light was being stretched and reddened by the immense gravitational field, exactly as Einstein's theory of relativity predicted it should be. The mathematics were inescapable. Only one thing in the known universe could be so massive yet so compact, could command such gravitational authority while remaining completely dark. The center of our galaxy had to contain what scientists call a supermassive black hole, a region of space where matter has collapsed so completely that not even light can escape its gravitational grip. But calling Sagittarius A star simply a black hole is like calling the ocean simply wet. This cosmic leviathan contains more mass than 4 million of our suns, all compressed into a region smaller than the orbit of Mercury around our sun.
If you could somehow transport our entire solar system to this location, planets and all, the whole thing would fit inside Sagittarius A star several times over, with room to spare.
It's a concentration of matter so extreme that it warps the very fabric of space and time around it, creating what physicists describe as a gravitational well, so deep that anything falling in can never climb back out. The name itself carries a certain poetic weight. Sagittarius A star gets its designation from its location in the constellation Sagittarius, which ancient astronomers saw as a centaur archer drawing his bow. How fitting that the heart of our galaxy lies in the direction of the archer, as if the entire cosmos were taking aim at something just beyond our sight. The star suffix distinguishes it from other radio sources in the same region, though ironically, this particular star will never shine in any conventional sense. For decades, Sagittarius A star remained a phantom, detectable only through its gravitational influence on nearby stars and the radio waves generated by superheated matter spiraling around it. Scientists could measure its mass, track its effects, and study the light from objects falling into it, but the black hole itself remained stubbornly invisible, hidden behind what physicists call an event horizon, the point of no return beyond which nothing, not even light, can escape. This invisibility isn't a flaw in our telescopes or a limitation of our technology. It's a fundamental feature of black holes themselves. By definition, they don't emit light because light cannot escape from them. They're visible only in silhouette, like cosmic shadows cast against the glowing backdrop of space around them. For years, this shadow remained too small and too distant for even our most powerful instruments to resolve. But then, in the early 2000s, an ambitious international collaboration began taking shape. Scientists from around the world started linking radio telescopes across multiple continents, creating what they called the Event Horizon Telescope. By synchronizing observations from Hawaii to Chile to Antarctica, they could effectively create a telescope as large as planet Earth itself, with the resolution needed to peer into the heart of darkness at our galaxy's center. The technical challenges were staggering. They had to account for the rotation of the Earth, the atmosphere's interference, and the precise timing needed to coordinate observations across vast distances. They were essentially trying to photograph something that by its very nature cannot be photographed, looking for a shadow that measures just 50 microarcseconds across in our sky. To put that in perspective, it's like trying to spot a tennis ball on the moon while standing on Earth. The data they collected was so complex that it took years to process. Teams of scientists worked around the clock, developing new algorithms and computational techniques to extract an image from the radio waves they had captured. They were literally teaching computers how to see the unseeable, to find patterns in the electromagnetic whispers emanating from the edge of a black hole 26,000 light-years away. And then, on May 12, 2022, the impossible became visible. For the first time in human history, we laid eyes on Sagittarius A star, not the black hole itself, which remains forever hidden behind its event horizon, but its shadow, surrounded by a glowing ring of superheated matter spiraling around it at tremendous speeds. The image was blurry and distorted, like looking at a reflection in troubled water, but it was unmistakably real. We were seeing the silhouette of a monster that had lurked unseen at the heart of our galaxy for billions of years. The photograph revealed something remarkable about the nature of this cosmic giant. The glowing ring of matter around Sagittarius A star wasn't uniform. It had bright spots and dimmer regions, areas where the superheated gas was glowing more intensely than others. These variations told a story of incredible violence and energy, of matter being stretched and compressed by gravitational forces beyond anything we experience on Earth. As gas and dust fall toward the black hole, they don't simply disappear quietly into the darkness. Instead, they form what astronomers call an accretion disk, a swirling maelstrom of matter that heats up to millions of degrees as it spirals inward. The friction and magnetic fields in this cosmic whirlpool accelerate particles to nearly the speed of light, causing them to emit intense radiation across the electromagnetic spectrum. It's like watching a cosmic campfire, except the fuel being consumed is the very fabric of space and time itself. What makes Sagittarius A star particularly fascinating is how relatively quiet it is for such a massive black hole. Many supermassive black holes in other galaxies are voracious eaters, constantly devouring matter and shooting jets of high-energy particles across thousands of light-years. Our galactic center, by comparison, is almost hibernating. It's not actively feeding on large amounts of matter, which is actually quite fortunate for us. If Sagittarius A star were more active, the radiation it would produce could make large portions of our galaxy uninhabitable. This gentle giant at our galaxy's heart plays a role far more subtle and profound than simple destruction. Its gravitational influence extends across the entire Milky Way, helping to maintain the elegant spiral structure we see in other galaxies like ours. Stars throughout our galaxy feel its pull, and their orbits are subtly influenced by this central mass. In a very real sense, Sagittarius A star is the conductor of a cosmic orchestra, with billions of stars dancing to the rhythm of its gravitational symphony. The symphony that Sagittarius A star conducts across our galaxy raises a profound question about the nature of these cosmic giants. How does something that devours light itself become the organizing principle for billions of stars? How can an object defined by its ability to trap everything that ventures too close simultaneously serve as the gravitational anchor that holds our entire galaxy together? The answer lies in understanding the delicate balance between destruction and creation that governs the behavior of supermassive black holes. To truly appreciate this cosmic paradox, we need to step back and consider what a black hole actually is. The term itself can be misleading, conjuring images of a cosmic vacuum cleaner sucking up everything in sight. But black holes are far more subtle and elegant than that popular conception suggests. They are regions of space where matter has become so densely concentrated that it warps the fabric of space-time itself beyond recognition. Imagine space-time as a vast rubber sheet stretched tight across an enormous frame. Now picture placing a bowling ball in the center of that sheet. The heavy ball creates a depression and if you roll marbles across the sheet, they curve around the dip rather than traveling in straight lines. This is essentially how gravity works according to Einstein's theory of general relativity. Massive objects bend space-time, and that curvature is what we experience as gravitational force. But now imagine pressing that bowling ball deeper and deeper into the rubber sheet, making the depression steeper and more pronounced. Eventually, you might push so hard that you create a hole that goes all the way through the sheet, a region where the curvature becomes so extreme that anything rolling into it cannot roll back out. That's analogous to what happens when matter collapses to form a black hole. The boundary around this point of no return is called the event horizon, and it represents one of the most fascinating frontiers in all of physics. Cross this invisible threshold, and you've entered a realm where the normal rules of cause and effect begin to break down. Light emitted from inside the event horizon can never escape to reach the outside universe. Time itself behaves strangely, slowing down relative to the outside world as you approach the horizon, until at the boundary itself, time appears to stop completely from the perspective of distant observers. What makes Sagittarius A star particularly remarkable is not just its size, but the way it influences everything around it without actually consuming very much material. Think of it as a cosmic lighthouse keeper, maintaining order through its gravitational presence rather than through active feeding. The black hole sits quietly at the center of our galaxy, its massive gravitational field providing the stable foundation upon which the entire galactic structure rests. This stability is crucial for the formation and evolution of galaxies like our own. Without a central supermassive black hole, galaxies tend to be chaotic places where stars are flung around randomly, never settling into the elegant spiral patterns we observe. The central black hole acts like a cosmic weight that keeps everything properly organized, allowing spiral arms to form and persist over billions of years. But the relationship between Sagittarius A star and our galaxy extends far beyond simple gravitational anchoring. The black hole also plays a crucial role in regulating star formation throughout the Milky Way, through a process that astronomers call feedback. When matter does occasionally fall into the black hole, it doesn't disappear quietly. Instead, it forms that glowing accretion disk we discussed earlier, heating up to millions of degrees and emitting intense radiation across the electromagnetic spectrum. This radiation, along with powerful jets of particles that can be launched from the vicinity of the black hole, acts like a cosmic thermostat for the entire galaxy. When too much gas begins accumulating in the galactic center, threatening to trigger a burst of rapid star formation, the increased activity around Sagittarius A star heats up and disperses the gas, slowing down the rate at which new stars are born. It's a self-regulating system that helps maintain the delicate balance necessary for a galaxy like ours to evolve steadily over cosmic time. The discovery of this central organizing principle has revolutionized our understanding of how galaxies form and evolve. Astronomers now realize that virtually every large galaxy in the universe contains a supermassive black hole at its center, and there's a remarkably tight relationship between the mass of these black holes and the properties of their host galaxies. Larger galaxies tend to have more massive central black holes, and the ratio between black hole mass and galaxy mass remains surprisingly constant across a wide range of galactic types and sizes. This correlation suggests that galaxies and their central black holes grew up together, influencing each other's development over billions of years of cosmic evolution. It's not that galaxies formed first and then somehow acquired black holes later, or that black holes formed first and then gathered galaxies around them. Instead, the two appear to have co-evolved in a complex dance of mutual influence that astronomers are still working to understand completely. The process by which supermassive black holes, like Sagittarius A star, originally formed remains one of the great mysteries in astrophysics. We know that stellar mass black holes form when individual massive stars reach the end of their lives and collapse under their own gravity. But stellar black holes typically contain only a few times the mass of our Sun, nowhere near the millions of solar masses found in supermassive black holes. One possibility is that the first generation of stars in the early universe was much more massive than the stars we see today, and when these primordial giants died, they left behind black hole seeds that were already quite substantial. these seeds could then have grown over billions of years by accreting matter from their surroundings and merging with other black holes as galaxies collided and combined. Another intriguing possibility is that supermassive black holes formed directly from the collapse of massive gas clouds in the early universe, without ever going through a stellar phase. Computer simulations suggest that under the right conditions, enormous clouds of primordial hydrogen and helium could have collapsed directly into black holes, containing thousands or even millions of solar masses, right from the start. The truth is probably some combination of these processes, with different supermassive black holes forming through different pathways depending on the specific conditions in their local environments. What seems certain is that these cosmic giants were already in place when the universe was much younger than it is today. Astronomers have discovered supermassive black holes in galaxies, so distant that we're seeing them as they were when the universe was less than 1 billion years old, which means they formed very early in cosmic history. Understanding the formation and evolution of supermassive black holes has important implications for our understanding of the universe as a whole. These objects serve as cosmic archaeologists, preserving information about the conditions that existed in the early universe. By studying their properties and distribution, astronomers can learn about the processes that shaped the cosmos during its first billion years, when the first galaxies were forming and the universe was transitioning from a simple, nearly uniform state to the complex structure we observe today. The relationship between Sagittarius A star and our own existence is more intimate than you might expect. The stable galactic environment created by our central black hole has allowed our solar system to maintain a relatively safe orbit in the galaxy's suburbs for over 4.5 billion years. We're positioned in what astronomers call the galactic habitable zone, far enough from the dangerous radiation of the galactic center, but not so far out that we're isolated from the heavy elements created by stellar nucleosynthesis. This cosmic location has been crucial for the development of life on Earth. If we were much closer to the galactic center, the intense radiation environment would likely have sterilized our planet multiple times over the course of its history. If we were much farther out, our solar system might never have acquired the heavy elements necessary for rocky planet formation and biological chemistry. The gravitational influence of Sagittarius A star also helps maintain the stability of stellar orbits throughout the galaxy. Without this central organizing force, the orbital motions of stars would be more chaotic, leading to more frequent close encounters between stellar systems. Such encounters could disrupt planetary orbits, potentially ejecting planets from their star systems or sending them careening into their parent stars. Even the timing of our solar system's formation appears to have been influenced by the galactic environment shaped by our central black hole. The Sun formed during a period when the galaxy had reached a certain level of chemical maturity, with enough heavy elements to form rocky planets, but not so much activity in the galactic center that the radiation environment was hostile to planetary formation. Recent advances in gravitational wave astronomy have opened up entirely new ways of studying black holes and their role in cosmic evolution. When two black holes spiral into each other and merge, they create ripples in space-time itself that can be detected by instruments like LIGO and Virgo. These gravitational wave detections have revealed a previously unknown population of stellar mass black holes and provided new insights into how black holes form and evolve. While we haven't yet detected gravitational waves from supermassive black hole mergers like the ones that would occur when galaxies collide, future space-based gravitational wave detectors should be sensitive enough to observe these cosmic events. Such observations will provide unprecedented insights into how supermassive black holes like Sagittarius A star formed and grew over cosmic time. The study of our galactic center has also revealed the incredible precision required for life to exist in our universe. The mass of Sagittarius A star, the structure of our galaxy, and our position within it all had to fall within relatively narrow ranges for our solar system to enjoy the stable, long-term environment necessary for biological evolution. It's a reminder that we exist not just on a pale blue dot suspended in space, but as part of an intricate cosmic ecosystem where even the most seemingly destructive forces play essential constructive roles. As we drift deeper into our exploration of this cosmic giant, we begin to appreciate that Sagittarius A star is not simply a monster lurking in the darkness. It's the beating heart of our galactic home, an ancient engine of organization and stability that has helped create the conditions necessary for stars, planets, and ultimately life itself to flourish. In the gentle gravitational embrace of this invisible giant, billions of stories unfold across the cosmos, including our own quiet tale of wonder and discovery. The story of how we finally captured that first image of Sagittarius A star is itself a tale of human persistence that spans decades, involving hundreds of scientists scattered across the globe, working together to accomplish something that seemed impossible just a generation ago. It's a reminder that some of the most profound discoveries in science come not from sudden flashes of inspiration, but from the patient accumulation of knowledge, the gradual improvement of technology, and the willingness to chase an idea even when success seems impossibly distant. The journey began long before anyone had even conceived of photographing a black hole directly. In the early 1960s, astronomers first detected intense radio emissions coming from the galactic center, but they had no idea what was producing them. The technology simply didn't exist to resolve fine details at such enormous distances. It was like trying to read a book from across a football field while wearing someone else's glasses. You might know something interesting was there, but the specifics remained frustratingly out of reach. Radio astronomy itself was still a relatively young field. Having emerged from radar technology developed during World War II, scientists had discovered that celestial objects emit radio waves in addition to visible light, opening up an entirely new window on the universe. But radio telescopes in those early days were crude instruments compared to what we have today, capable of detecting radio sources but unable to pinpoint their exact locations or study their detailed structure. The breakthrough came with the development of a technique called very long baseline interferometry, which sounds complicated but relies on a beautifully simple principle. Instead of building one enormous radio telescope, which would be prohibitively expensive and technically challenging, astronomers learned to link multiple smaller telescopes together electronically, creating a virtual telescope as large as the distance between the individual instruments. The process works because radio waves, like all forms of light, travel in synchronized patterns. When the same celestial radio source is observed simultaneously by telescopes separated by hundreds or thousands of miles, the tiny timing differences in when the radio waves arrive at each location contain information about the structure of the source. It's similar to how your brain uses the slight delay between sound reaching your left and right ears to determine which direction a sound is coming from, except vastly more precise and complex. By the 1970s and 80s, networks of radio telescopes were beginning to reveal details about cosmic radio sources that had never been seen before. Astronomers discovered that many galaxies have incredibly narrow jets of high-energy particles streaming away from their centers at nearly the speed of light. They found that some radio sources are incredibly compact, smaller than our solar system, yet more energetic than entire galaxies. And at the center of our own galaxy, they detected a radio source that was both extremely bright and remarkably compact. This object, initially catalogued as Sagittarius A star, became one of the most intensively studied radio sources in the sky. As interferometry techniques improved and more telescopes joined the networks, the radio structure around our galactic center came into sharper focus. Scientists could see that the radio emission wasn't coming from a diffuse cloud of gas, but from a very specific, tiny region at the exact gravitational center of our galaxy. The theoretical framework for understanding these observations was developing in parallel. Einstein's equations had predicted the existence of black holes as early as 1916, but for decades they remained mathematical curiosities rather than physical realities. It wasn't until the 1960s that physicists began to seriously consider that such objects might actually exist in nature. The term black hole itself was coined by physicist John Wheeler in 1967, and it captured the public imagination in a way that more technical descriptions never could. Here was an object so extreme that it defied common sense, a region of space where the familiar rules of physics broke down completely. Light, the fastest thing in the universe, couldn't escape. Time ran differently. Space itself was twisted into impossible geometries. As theoretical understanding of black holes advanced, astronomers began to realize that these exotic objects might not be as rare as originally thought. If massive stars could collapse to form stellar mass black holes, then perhaps the supermassive objects detected at galactic centers were simply scaled-up versions of the same phenomenon. The radio emissions could be explained as radiation from superheated matter spiraling into these cosmic giants just before crossing the point of no return. But there was still an enormous gap between theoretical prediction and observational confirmation. Detecting the gravitational influence of a black hole was one thing. Actually seeing the black hole itself, or at least its shadow, was quite another. The resolution required was mind-boggling. Sagittarius A star subtends an angle in our sky of only about 50 microarcseconds, roughly equivalent to viewing a tennis ball on the moon from Earth. No single telescope on Earth, no matter how large, could achieve such resolution. The fundamental physics of radio waves places limits on how sharp an image any individual instrument can produce. To see details as fine as the shadow of our galactic black hole would require a telescope roughly the size of our entire planet. This seemingly impossible requirement led to one of the most ambitious scientific collaborations in history. Starting in the early 2000s, radio astronomers began seriously planning what they called the Event Horizon Telescope, a planet-spanning network of radio observatories that would work together as a single Earth-sized instrument. The technical challenges were staggering. Each participating telescope had to be equipped with ultra-precise atomic clocks to synchronize their observations down to tiny fractions of a second. The data from each site had to be recorded on specially designed hard drives and physically shipped to central processing facilities because the volume of information was too great for internet transmission. Weather conditions at all sites had to be acceptable simultaneously, which meant coordinating observations across multiple continents and climate zones. Even more challenging was the data analysis. The raw observations from the Event Horizon Telescope don't look like photographs. Instead, they consist of complex patterns of radio interference that must be decoded using sophisticated algorithms. It's rather like trying to reconstruct a symphony from the echoes you hear in a concert hall, except the original music is playing at frequencies your ears can't detect, and the concert hall is 26,000 light-years away. The process of converting these radio interference patterns into actual images required the development of entirely new computational techniques. Different teams of scientists worked independently, using different algorithms and approaches to ensure that any features in the final image were real, rather than artifacts of the data processing. They were essentially teaching computers how to see something that had never been seen before. The observations themselves took place over several nights in April 2017, when weather conditions were favorable at enough sites to create the necessary global baseline. For a few precious hours, telescopes in Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica all pointed toward the same patch of sky, recording the faint radio whispers from the edge of our galactic black hole. What followed was years of painstaking analysis. The data was so complex that multiple independent teams worked on it simultaneously, each developing their own imaging algorithms and cross-checking their results. The goal was to ensure that any structure they detected in the radio emissions was actually coming from Sagittarius A star, rather than being introduced by their analysis techniques. The challenge was compounded by the fact that the region around Sagittarius A star is incredibly dynamic. Unlike some other supermassive black holes that maintain relatively stable accretion patterns, our galactic center shows significant variability on timescales of minutes to hours. The hot gas swirling around the black hole changes brightness and position constantly, like trying to photograph a constantly shifting kaleidoscope. This variability actually provided additional information about the physics near the black hole, but it made the imaging process much more complex. The astronomers had to develop techniques for averaging out the rapid changes while preserving the underlying structure of the accretion flow and the black hole shadow itself. The breakthrough came in early 2022, when the various analysis teams achieved convergent results, Despite using different computational approaches and independent data processing pipelines, they were all seeing the same basic structure: a bright ring of radio emission surrounding a dark central region. The shadow of Sagittarius A star had finally been captured. The image that emerged from this years-long effort was blurry and distorted, nothing like the crisp photographs we're accustomed to from space telescopes observing invisible light, but it was unmistakably real, showing the characteristic donut-shaped structure predicted by Einstein's equations for the space around a rotating black hole. The dark region in the center is the shadow of the black hole itself, the area from which no light can escape to reach our telescopes. It's a direct glimpse of the boundary between the known universe and the unknowable realm beyond the event horizon. What made the achievement even more remarkable was that the observed shadow matched theoretical predictions with stunning accuracy. The size of the dark region corresponded exactly to what Einstein's equations predicted for a black hole of Sagittarius A star's measured mass. The shape and brightness distribution of the surrounding ring showed clear signs of the extreme gravitational effects predicted by general relativity. For the first time in human history, we were looking directly at the edge of space-time itself, the place where matter and energy disappear from our universe forever. It was validation not just of our understanding of black holes, but of our entire theoretical framework for describing gravity, space, and time on the largest scales. The image also revealed subtle details about the rotation of Sagittarius A star and the dynamics of the matter falling into it. The bright spots in the ring weren't distributed randomly, but showed patterns consistent with hot gas being whipped around by the black hole's spin. These details provided new insights into how supermassive black holes interact with their surroundings and how they might have influenced the evolution of their host galaxies over cosmic time. Perhaps most importantly, the success of the Event Horizon Telescope demonstrated that human ingenuity and international cooperation could overcome seemingly impossible technical challenges. By working together across national boundaries and combining resources from around the globe, scientists had managed to peer into one of the most extreme environments in the universe and emerge with genuine understanding. The achievement of imaging Sagittarius A star opened a door that had been locked for centuries, revealing not just the shadow of our galactic black hole, but fundamentally changing how we think about these cosmic giants and their role in shaping the universe around them. The success of the Event Horizon Telescope marked the beginning of a new era in astronomy, one where we could finally observe directly the most extreme environments that nature has to offer, places where the familiar laws of physics are stretched to their absolute limits. What we discovered in that first image was both reassuring and profoundly mysterious. Reassuring because the shadow matched Einstein's predictions with remarkable precision, validating our theoretical understanding of gravity and space-time in the strongest possible terms. But mysterious because it also raised new questions about the detailed behavior of matter and energy in these extreme environments. Questions that will likely keep scientists busy for decades to come. The structure visible in that historic photograph tells a story of incredible violence taking place in apparent slow motion. The bright ring surrounding the black hole's shadow represents matter that has been heated to temperatures of billions of degrees, far hotter than the core of the sun. This superheated gas, composed primarily of protons and electrons stripped apart by the intense environment, glows brilliantly across the electromagnetic spectrum as it spirals inexorably toward the point of no return. But the journey of this matter, from the cold depths of space to the blazing accretion disk around Sagittarius A star, is far from straightforward. Gas doesn't simply fall directly into a black hole like water going down a drain. Instead, it follows a complex orbital dance that can last thousands of years, gradually spiraling inward as it loses energy and angular momentum through friction and magnetic interactions. Think of it like water spiraling down a bathtub drain, except the bathtub is 26,000 light-years away. The water is composed of individual atoms moving at significant fractions of the speed of light. and the drain leads to a region where time itself slows down and eventually stops. The matter falling towards Sagittarius A star doesn't disappear instantly when it crosses the event horizon. From our perspective, watching from a safe distance, it appears to slow down and freeze at the boundary, its light growing redder and dimmer until it fades from view. This strange behavior arises from one of the most counterintuitive aspects of Einstein's theory of relativity. Time is not absolute or universal. It flows differently depending on how fast you're moving and how strong the gravitational field around you happens to be. Near a massive object like Sagittarius A star, time runs more slowly compared to regions of weaker gravity. The effect becomes more and more pronounced as you approach the black hole, until at the event horizon itself, time appears to stop completely from the perspective of distant observers. For the unfortunate matter actually falling into the black hole, however, the experience would be quite different. From its own perspective, it would pass through the event horizon in a finite amount of time, continuing its journey toward the central singularity where current physics breaks down completely. This divergence between different perspectives, between what distant observers see and what in falling matter experiences, is one of the most mind-bending aspects of black hole physics. The image captured by the Event Horizon Telescope also revealed details about the rotation of Sagittarius A star itself. Like most objects in the universe, our galactic black hole is spinning, and this rotation drags the surrounding space-time along with it, in a phenomenon physicists call frame dragging. The effect is subtle but measurable, causing the hot gas in the accretion disk to spiral around the black hole in patterns that would be impossible if the black hole were stationary. This spin has profound implications for how matter and energy behave in the vicinity of the black hole. A rotating black hole can extract energy from infalling matter more efficiently than a non-rotating one, and under certain circumstances, it can even give energy back to the surrounding environment through processes that seem to violate our everyday intuitions about conservation laws. These interactions between spinning black holes and their accretion disks are thought to be responsible for some of the most energetic phenomena in the universe, including the relativistic jets that stream away from certain types of galaxies at nearly the speed of light. The discovery also highlighted the remarkable precision with which we can now study these exotic objects. The Event Horizon Telescope didn't just confirm that Sagittarius A star exists and has roughly the mass that previous measurements suggested. It provided detailed information about the temperature, density, and velocity of matter in the immediate vicinity of the black hole, allowing astronomers to test theoretical models of accretion disk physics with unprecedented accuracy. One of the most surprising aspects of the observations was how quickly the structure around Sagittarius A star changes. Unlike some other supermassive black holes that maintain relatively stable accretion patterns, our galactic center shows dramatic variability on timescales of just hours or even minutes. Hotspots in the accretion disk appear, brighten, dim, and disappear in rapid succession, creating a constantly shifting pattern of emission that makes the region around our black hole one of the most dynamic environments in the known universe. This rapid variability provides a natural laboratory for studying the physics of matter under extreme conditions. By watching how the brightness and structure of the accretion disk change over time, astronomers can trace the motion of individual clumps of hot gas as they orbit the black hole, measuring their velocities and temperatures with extraordinary precision. These observations offer direct insights into how gravity behaves in the strong field regime, where Newton's laws break down and Einstein's more complex equations take over. The success of imaging Sagittarius A star has also sparked renewed interest in theoretical questions about the nature of black holes themselves. One of the most profound puzzles in modern physics is the information paradox, which arises from the apparent conflict between quantum mechanics and general relativity when applied to black holes. According to quantum theory, information cannot be destroyed, but according to classical black hole physics, anything that falls past the event horizon is lost forever when the black hole eventually evaporates through Hawking radiation. Recent theoretical work has suggested that the solution to this paradox might lie in the subtle structure of the event horizon itself. Some physicists propose that what we perceive as a smooth boundary might actually be a complex quantum mechanical surface that preserves information in ways we don't yet fully understand. The detailed observations of Sagittarius A star provide new data that theorists can use to test these ideas and develop more complete theories of quantum gravity. The imaging of our galactic black hole has also opened up new possibilities for studying fundamental physics in ways that are impossible in terrestrial laboratories. The extreme gravitational fields near Sagittarius A star create conditions where space-time itself becomes a participant in physical processes, not just a passive backdrop. By studying how light bends and redshifts as it passes through these regions, astronomers can test Einstein's equations in regimes where they've never been verified before. These tests are particularly important because they probe the foundations of our understanding of space, time, and gravity. If Einstein's theory were to fail in these extreme environments, it would point toward new physics beyond our current understanding, possibly providing clues about how to unify general relativity with quantum mechanics into a single, more complete theory of nature. The technological achievement, represented by the Event Horizon Telescope, has also inspired plans for even more ambitious projects. Astronomers are already working on proposals for space-based interferometers that could achieve even higher resolution, potentially allowing us to study the immediate vicinity of the event horizon in unprecedented detail. Such instruments might be able to detect the signatures of individual orbital motions in the accretion disk, or even observe the effects of quantum mechanics in the strong gravitational field environment. Looking ahead, the study of Sagittarius A star promises to remain at the forefront of astrophysical research for years to come. Each new observation adds another piece to the puzzle of how these cosmic giants form, evolve, and influence their surroundings. The black hole that once seemed like an exotic theoretical curiosity has become a natural laboratory where we can study some of the most fundamental questions in physics and astronomy. Perhaps most remarkably, this revolution in our understanding has come from studying an object that is, by definition, invisible. We cannot see Sagittarius A star directly because it emits no light. Instead, we've learned to read the stories written in the behavior of matter and energy around it, deciphering the gravitational signatures and electromagnetic whispers that reveal its presence and properties. It's a testament to human ingenuity that we've managed to study in such detail something that cannot be observed directly, using the light of its absence to illuminate some of the deepest mysteries of the cosmos. In the gentle glow of that first image, with its fuzzy ring of light surrounding a profound darkness, we see not just the shadow of a black hole, but a reflection of humanity's endless curiosity about the universe we inhabit. It's a reminder that even in the face of the most extreme and alien environments nature can produce, human reason and cooperation can still find ways to understand and appreciate the elegant complexity of the cosmos that surrounds us. The profound darkness at the center of that historic image speaks to one of the most fundamental questions in physics. What happens to matter and information when they cross the event horizon and disappear from our observable universe forever? This question has haunted physicists for decades, leading to some of the most intense debates in modern science and revealing deep connections between gravity, quantum mechanics, and the nature of information itself. To understand why this matters so much, we need to appreciate that black holes challenge our most basic assumptions about how the universe works. In our everyday experience, information is never truly lost. You might delete a file from your computer, but forensic experts can often recover it from traces left on the hard drive. You might burn a book, but in principle, if you could track every atom of smoke and ash, you could reconstruct the original text. This principle, that information is always conserved, is one of the foundational assumptions of quantum mechanics. But black holes seem to violate this rule in the most dramatic way possible. When matter falls past the event horizon of Sagittarius A star, it appears to disappear completely from our universe, taking with it all the information that described its quantum state. According to classical black hole physics, this information is lost forever when the black hole eventually evaporates through a process called Hawking radiation, named after the brilliant physicist Stephen Hawking, who first predicted it. Hawking radiation emerges from the quantum foam that exists everywhere in space, even in the apparently empty vacuum around black holes. At the quantum level, pairs of particles constantly pop into existence and annihilate each other in timescales so brief that they cannot be directly observed. But near a black hole's event horizon, something interesting happens to these virtual particle pairs. Occasionally, one particle from such a pair falls into the black hole while the other escapes, becoming real in the process and carrying away a tiny amount of the black hole's energy. Over enormous spans of time, this process causes black holes to slowly evaporate, shrinking gradually until they disappear completely in a final burst of radiation. For a supermassive black hole like Sagittarius A star, this process would take an almost incomprehensibly long time, far longer than the current age of the universe. But according to Hawking's original calculations, the radiation produced during this evaporation process would be completely random, carrying no trace of the information that originally fell into the black hole. This creates what physicists call the information paradox. If information really is lost when black holes evaporate, it would represent a fundamental violation of quantum mechanics, suggesting that our understanding of the microscopic world is incomplete or incorrect. But if information is somehow preserved and encoded in the Hawking radiation, it would require mechanisms that seem impossible according to our current understanding of general relativity. Recent theoretical breakthroughs have suggested that the resolution to this paradox might lie in the realization that the event horizon of a black hole is not the smooth, featureless boundary that classical physics describes. Instead, it might be a complex quantum mechanical surface that preserves information in subtle ways that we're only beginning to understand. Some physicists propose that the event horizon might be covered with quantum structures that they playfully call fuzz, microscopic details that could encode information about everything that has ever fallen into the black hole. Other theories suggest that black holes might be connected to parallel regions of space-time through structures called wormholes, allowing information to escape through pathways that bypass the event horizon entirely. These ideas push the boundaries of our understanding of space and time, suggesting that the universe might be far stranger and more interconnected than we ever imagined. The study of Sagittarius A star provides a natural laboratory for testing these ideas. The Event Horizon Telescope observations have revealed details about the structure of space-time near the black hole that can be compared with theoretical predictions from various quantum gravity theories. While we're still far from resolving the information paradox, each new observation adds another piece to the puzzle, bringing us closer to understanding how quantum mechanics and general relativity might be unified into a single, more complete theory of nature. The implications of these investigations extend far beyond academic physics. Understanding the true nature of black holes could revolutionize our comprehension of how information, space, and time interact at the most fundamental level. It might reveal that our universe is part of a larger structure, connected to other regions of space-time in ways we haven't yet discovered. It could even provide insights into the ultimate fate of the universe itself, and what happens to information and consciousness in a cosmos that seems destined to expand and cool forever. The gravitational effects of Sagittarius A star also provide a unique window into the behavior of space and time under extreme conditions. Near the black hole, the fabric of space-time is warped so severely that it creates what physicists call gravitational time dilation. Clocks run more slowly in stronger gravitational fields, and near Sagittarius A star, this effect becomes dramatic enough to measure with precision instruments. If you could somehow survive a journey to the vicinity of our galactic black hole, carrying a precise clock with you, you would find that it runs noticeably slower compared to identical clocks back on Earth. The effect becomes more pronounced the closer you get to the event horizon, until at the boundary itself, time would appear to stop completely from the perspective of distant observers. This isn't science fiction or a failure of our clocks. It's a fundamental feature of how time behaves in the presence of strong gravitational fields. This time, dilation has practical implications for understanding the behavior of matter in the accretion disk around Sagittarius A star. The hot gas, spiraling toward the black hole, experiences different rates of time, depending on its distance from the event horizon, leading to complex synchronization effects that influence how the material radiates energy. The bright spots visible in Event Horizon Telescope images are partly a result of these relativistic effects, creating patterns of emission that would be impossible in the weak gravitational fields we're familiar with on Earth. The study of these temporal effects also provides tests of Einstein's theory of general relativity in regimes where it has never been verified before. By measuring how light from the accretion disk is redshifted and time-delayed as it climbs out of the black hole's gravitational well, astronomers can verify that gravity behaves exactly as Einstein predicted, even in these extreme environments. So far, every measurement has confirmed the theory's predictions with remarkable accuracy, but each new test pushes the boundaries of our confidence in our understanding of spacetime. The magnetic fields around Sagittarius A star add another layer of complexity to this already exotic environment. The hot, ionized gas in the accretion disk carries embedded magnetic field lines that get twisted and amplified as the material spirals inward. These magnetic fields can become so strong that they dominate the dynamics of the accretion flow, channeling matter into narrow streams and potentially launching high-speed jets of particles away from the black hole. While Sagittarius A star doesn't currently display the dramatic jets seen around some other supermassive black holes, traces of past activity suggest that our galactic center has experienced more violent episodes in its history. Radio observations have revealed bubble-like structures extending thousands of light years above and below the galactic plane, possibly remnants of ancient jets or outflows that occurred when the black hole was more actively feeding. These magnetic phenomena are crucial for understanding how black holes interact with their surroundings and influence the evolution of their host galaxies. The energy released by magnetic processes in accretion disks can heat and disperse nearby gas clouds, regulating star formation throughout the galaxy. In some cases, powerful jets launched by supermassive black holes can travel for millions of light years, depositing energy in the intergalactic medium and affecting the formation of other galaxies. The rotation of Sagittarius A star itself adds yet another dimension to these complex interactions. Like a cosmic engine, the spinning black hole can extract energy from infalling matter through a process called the Penrose mechanism, named after mathematician Roger Penrose, who first described it. In this process, matter falling into the ergosphere, a region just outside the event horizon where space-time itself is dragged around by the black hole's rotation, can actually gain energy and escape with more momentum than it had originally. This mechanism allows rotating black holes to be more efficient engines than their non-rotating counterparts, extracting up to 42% of the rest mass energy of infalling matter and converting it into radiation and kinetic energy. For comparison, nuclear fusion in stars converts less than 1% of mass into energy, making black holes potentially the most efficient energy sources in the universe. The implications of this efficiency extend to understanding how galaxies form and evolve over cosmic time. The energy output from supermassive black holes during their active phases can exceed the total energy output of all the stars in their host galaxies combined. This feedback mechanism plays a crucial role in regulating galaxy growth, preventing runaway star formation that would quickly exhaust the available gas supply. Recent computer simulations have shown that galaxies without central supermassive black holes evolve very differently from those with these massive regulators. Without the feedback effects from black hole activity, galaxies tend to form stars too rapidly and burn through their gas reserves, leading to stellar populations that are much older and more metal-rich than what we observe in real galaxies. The presence of supermassive black holes like Sagittarius A star appears to be essential for creating the diverse range of galaxy types we see in the universe today. This intimate connection between black holes and galaxy evolution has led astronomers to recognize that studying objects like Sagittarius A star is not just about understanding exotic physics in extreme environments. It's about comprehending how the universe itself has developed from the simple, nearly uniform state revealed by the cosmic microwave background to the rich tapestry of structure we observe today. Every supermassive black hole is both a product of cosmic evolution and an agent of that evolution, shaping the development of matter and energy on the largest scales. The story of how Sagittarius A star came to exist in the first place takes us back to the very earliest chapters of cosmic history, to a time when the universe was young, hot, and filled with possibilities that we can barely imagine today. Understanding the formation and growth of our galactic black hole requires us to journey backward through billions of years to an epoch when the first stars were beginning to shine and the first galaxies were taking shape in the cooling darkness of primordial space. When the universe was less than 1 billion years old, it was a very different place from the structured cosmos we observe today. There were no spiral galaxies with elegant arms sweeping through space, no well-established galactic neighborhoods where solar systems could form and evolve in relative peace. Instead, the early universe was a chaotic realm of colliding gas clouds, merging proto-galaxies, and the first generation of massive stars living fast and dying young in spectacular explosions that seeded space with the heavy elements necessary for complex chemistry. In this primordial environment, the ancestors of supermassive black holes like Sagittarius A* were taking their first steps toward existence. But exactly how these cosmic giants formed remains one of the most challenging puzzles in astrophysics. The problem is one of scale and timing. We know that stellar mass black holes form when individual massive stars collapse at the end of their lives. But even the most massive stars produce black holes containing only dozens of solar masses, nowhere near the millions of solar masses found in supermassive black holes. Growing from stellar mass seeds to supermassive proportions requires either incredibly efficient feeding over billions of years, or alternatively, some mechanism for creating much more massive black hole seeds right from the start. The mathematics of black hole growth suggest that even under the most favorable conditions, stellar mass seeds would struggle to reach supermassive proportions within the time available in the early universe. This realization has led theorists to propose more exotic formation scenarios for the first supermassive black holes. One possibility is that they formed directly from the collapse of massive gas clouds in the early universe, without ever going through a stellar phase. Computer simulations suggest that under the right conditions, clouds containing tens of thousands of solar masses of primordial hydrogen and helium could have collapsed directly into black holes, providing much larger seeds for subsequent growth. These direct collapse scenarios require very specific conditions to work. The gas clouds must be massive enough to overcome their own internal pressure and collapse catastrophically, but they must also avoid fragmenting into smaller pieces that would form individual stars instead of a single massive black hole. The delicate balance required suggests that direct collapse black holes might have been relatively rare in the early universe, forming only in special environments where the conditions were just right. Another possibility is that the first generation of stars was fundamentally different from the stars we see today. These population 3 stars, as astronomers call them, formed from gas that contained no heavy elements, only the hydrogen and helium produced during the Big Bang. Without heavy elements to help cool the gas clouds during star formation, these primordial stars might have been much more massive than modern stars, potentially containing hundreds or even thousands of solar masses. When such massive stars reached the end of their brief lives, they would have collapsed into correspondingly massive black holes, providing much larger seeds for subsequent growth. These intermediate mass black holes could then have grown relatively quickly through accretion and mergers, reaching supermassive proportions within the first billion years of cosmic history. The growth phase of early supermassive black holes was likely a much more violent and dramatic process than what we observe around Sagittarius A* today. In the dense, gas-rich environment of the early universe, black holes had access to abundant fuel for rapid growth. Instead of the relatively gentle, sporadic feeding we see in our galactic center, early supermassive black holes probably experienced sustained periods of intense accretion, growing rapidly while shining as brilliant quasars that could be seen across the observable universe. These quasar phases represent some of the most energetic phenomena in the cosmos. A single supermassive black hole in its active phase can outshine the combined light of hundreds of billions of stars, making it visible at distances of billions of light years. The energy comes from the gravitational potential energy of matter falling into the black hole, converted to radiation with an efficiency that no other known process can match. But this rapid growth phase couldn't continue indefinitely. As supermassive black holes grew larger and more massive, their own energy output began to affect their surroundings in ways that limited further growth. The intense radiation from matter falling into the black hole heated and dispersed nearby gas clouds, reducing the fuel available for continued accretion. At the same time, powerful jets of high-energy particles launched from the vicinity of the black hole could blow away gas from the surrounding galaxy, effectively starving the black hole of additional material. This self-regulation mechanism explains why most supermassive black holes, including Sagittarius A*, are relatively quiet today compared to their ancient quasar ancestors. After an initial period of rapid growth and intense activity, they reached a kind of equilibrium with their surroundings, settling into the more sedate feeding patterns we observe in the modern universe. The transition from active quasar to quiet supermassive black hole wasn't necessarily smooth or permanent. Throughout cosmic history, galaxies have continued to merge and collide, occasionally delivering fresh supplies of gas to previously dormant black holes and triggering new episodes of activity. Even today, astronomers observe galaxies in the process of merging, their central black holes spiraling toward each other in a cosmic dance that will eventually culminate in their coalescence into an even more massive black hole. These merger events are among the most spectacular phenomena predicted by general relativity. When two supermassive black holes finally come together, they create ripples in space-time itself, gravitational waves that carry away enormous amounts of energy and can be detected by sensitive instruments even at distances of billions of light-years. While current gravitational wave detectors are primarily sensitive to mergers between stellar mass black holes, future space-based instruments should be able to observe the coalescence of supermassive black holes like Sagittarius A*. The history of our own galaxy bears the scars of such violent encounters. Astronomical observations reveal streams of stars that appear to be the remnants of smaller galaxies that were torn apart and absorbed by the Milky Way over billions of years. Each such merger would have brought its own central black hole along for the ride, either adding to the mass of Sagittarius A* or being ejected from the galactic center through complex gravitational interactions. The current mass and properties of Sagittarius A* thus represent the end result of billions of years of cosmic evolution, growth through accretion, and mergers with other black holes. Its relatively quiet state today suggests that our galaxy has reached a mature phase of its evolution, with most of the available gas either incorporated into stars or dispersed by previous episodes of black hole activity. But this quiescent state doesn't mean that Sagittarius A* has stopped evolving. Even now, it continues to grow slowly through the occasional capture of individual stars that venture too close, and through the gradual accretion of diffuse gas from the surrounding interstellar medium. These processes occur on timescales much longer than human civilization, but they represent the ongoing evolution of our galactic center. The study of Sagittarius A* also provides insights into the future evolution of our galaxy and others like it. As the universe continues to expand and cool, the supply of fresh gas available for star formation and black hole feeding will gradually diminish. Galaxies will use up their remaining gas reserves, star formation will slow and eventually cease, and supermassive black holes will enter an even more dormant phase than we observe today. Eventually, in the far distant future, even the process of stellar evolution will come to an end as the longest-lived stars burn through their nuclear fuel and fade away. Slowly evaporating through Hawking radiation over timescales that dwarf the current age of the cosmos. But that distant future is almost incomprehensibly far away. For now, Sagittarius A* continues its ancient role as the gravitational anchor of our galaxy, maintaining the elegant spiral structure that has provided a stable environment for billions of years of stellar and planetary evolution. The fact that we exist to study and contemplate this cosmic giant is itself a testament to the delicate balance of forces that has allowed complex structures like galaxies, stars, and life itself to emerge from the simple, initial conditions of the early universe. In tracing the history of Sagittarius A star from its mysterious origins in the early cosmos to its current state as the quiet giant at our galaxy's heart, we're really telling the story of cosmic evolution itself. It's a narrative that spans billions of years and involves some of the most extreme physics imaginable. Yet it all leads to this moment when conscious beings on a small planet can turn their telescopes toward the galactic center and glimpse the shadow of infinity itself. The ancient light that allows us to study Sagittarius A star began its journey when the universe was young and chaotic, traveling for eons through expanding space to reach our instruments today. In that light, we can read the history of our galaxy, the story of how order emerged from chaos, and the ongoing dance between creation and destruction that continues to shape the cosmos around us. This dance between creation and destruction that we see written in the light from our galactic center becomes even more fascinating when we turn our attention to the immediate stellar neighborhood surrounding Sagittarius A star. Here, in the most extreme gravitational environment accessible to our telescopes, we find a community of stars unlike anything else in our galaxy, objects that have been shaped and sculpted by their proximity to the cosmic giant that dominates their existence. The stars that orbit closest to Sagittarius A star live lives of extraordinary intensity. They race around the black hole in elliptical paths that bring them breathtakingly close to the event horizon, experiencing gravitational forces that would tear apart any normal stellar system. These stellar daredevils, catalogued with designations like S2, S5, and S14, have become some of the most intensively studied objects in astronomy, providing natural laboratories for testing our understanding of gravity in its most extreme manifestations. Consider the remarkable journey of S2, perhaps the most famous of these galactic center stars. Every 16 years, this star completes a full orbit around Sagittarius A star, swinging from a distance of about 120 times the Earth-Sun distance at its farthest point to just 120 times that same distance at its closest approach. When it reaches this inner turning point of its orbit, S2 is traveling at more than 7,600 kilometers per second, fast enough to circle the Earth in less than 6 seconds. At these speeds and in such intense gravitational fields, the familiar physics of everyday experience gives way to the strange predictions of Einstein's relativity. The star's light becomes noticeably redshifted as it climbs out of the black hole's gravitational well, its wavelength stretched by the curvature of space-time itself. The star's orbital motion also shows subtle deviations from what Newton's laws would predict, exhibiting a phenomenon called relativistic precession, where the entire orbit slowly rotates over time. These effects, while tiny compared to the overall orbital motion, are measurable with modern astronomical instruments and provide some of the most stringent tests of general relativity ever conducted. Each time S2 completes an orbit, astronomers can verify that gravity behaves exactly as Einstein predicted, even in these extreme conditions where the theory has never been tested before. But the stars around Sagittarius A star don't just serve as passive test particles for studying gravity. They also tell a remarkable story about stellar evolution in extreme environments. Most of these close-orbiting stars are young, massive objects that shouldn't exist so close to the galactic center, according to conventional theories of star formation. The intense tidal forces near the black hole should prevent gas clouds from collapsing to form new stars. Yet, somehow these stellar neighbors manage to form and survive in this hostile environment. One possibility is that these stars formed much farther from the black hole and were subsequently captured through gravitational interactions with other stars, or stellar remnants. In this scenario, a binary star system might have wandered too close to Sagittarius A star, with one member of the pair being captured into a tight orbit while the other was flung away at high speed. This process could explain how young stars ended up so close to the black hole, while accounting for the observed population of high-velocity stars that have been ejected from the galactic center. Alternatively, some of these stars might have formed in place through processes that we don't yet fully understand. The environment near Sagittarius A star is so extreme that it might permit exotic star formation mechanisms that are impossible elsewhere in the galaxy. Dense clumps of gas in the accretion disk around the black hole might occasionally become massive enough to collapse under their own gravity, forming stars directly in the immediate vicinity of the event horizon. The fate of these stellar companions adds another layer of drama to the story of our galactic center. Over time, stellar winds and tidal forces will gradually strip away the outer layers of these stars, feeding additional material to the black hole and causing them to lose mass and orbital energy. Eventually, they will spiral inward until they cross the event horizon and disappear from our observable universe. But this process of stellar consumption isn't necessarily violent or sudden. For most stars, the journey from stable orbit to final plunge would take millions or billions of years, during which the star would gradually lose mass and brightness as it slowly spirals inward. Only if a star ventured extremely close to the black hole would it be torn apart dramatically by tidal forces, creating a brief but spectacular flare of X-rays and gamma rays as the stellar debris heats up and glows before disappearing beyond the event horizon. These stellar disruption events, while rare, provide astronomers with unique opportunities to study the immediate vicinity of black holes. When a star gets too close to Sagittarius A star and is torn apart by tidal forces, about half of the stellar material typically falls into the black hole while the other half is ejected at high speeds, creating a temporary accretion disk that glows brightly across the electromagnetic spectrum. The study of these events has revealed important details about the structure and composition of stars, the behavior of matter under extreme gravitational stress, and the dynamics of accretion onto black holes. Each stellar disruption is like a natural experiment that probes physics in regimes that cannot be reproduced in any terrestrial laboratory. Looking beyond the immediate stellar neighborhood, Sagittarius A star's influence extends throughout the central regions of our galaxy, affecting the motion and evolution of stars across a volume spanning hundreds of light-years. The gravitational field of the black hole creates what astronomers call a sphere of influence, a region where the black hole's gravity dominates over the collective gravitational pull of all the surrounding stars. Within this sphere of influence, stellar orbits become increasingly eccentric and randomly oriented as the central mass of the black hole overwhelms the more distributed gravitational effects of the stellar population. Stars that venture into this region experience gravitational interactions that can dramatically alter their trajectories, sometimes flinging them out of the galactic center at high speeds, or causing them to plunge inward toward eventual destruction. The boundary of this sphere of influence marks a transition zone where the organized, nearly circular orbits typical of disk galaxies give way to the chaotic, three-dimensional stellar motions characteristic of galactic centers. Understanding this transition is crucial for comprehending how supermassive black holes influence the overall structure and evolution of their host galaxies. Recent observations have also revealed that the stellar population near Sagittarius A star shows unusual characteristics compared to stars in other parts of our galaxy. Many of the stars in the galactic center appear to be relatively young, despite the fact that star formation should be suppressed by the extreme gravitational environment. This suggests either that star formation can occur under more extreme conditions than previously thought, or that there are mechanisms for transporting young stars from other regions of the galaxy to the galactic center. The chemical composition of these central stars also shows distinctive patterns that reflect the unique environment in which they formed or evolved. Stars near Sagittarius A star tend to have enhanced abundances of certain heavy elements, possibly due to enrichment from material processed by previous generations of stars that were disrupted by the black hole or expelled in stellar winds. These observations hint at complex cycles of star formation, stellar evolution, and material recycling that operate in the immediate vicinity of supermassive black holes. The intense gravitational field and radiation environment near Sagittarius A star create conditions that accelerate many astrophysical processes, compressing the normal timescales of stellar evolution and galactic chemical evolution into much shorter periods. The magnetic fields threading through the galactic center add yet another dimension to this complex environment. The motion of ionized gas and plasma near Sagittarius A star generates powerful magnetic fields that can channel and accelerate particles to extremely high energies. These magnetic processes are thought to be responsible for many of the high-energy phenomena observed in the galactic center, including the emission of X-rays and gamma rays, that make this region one of the most energetic environments in our galaxy. The interplay between gravity, magnetic fields, and radiation near Sagittarius A star creates a natural laboratory for studying fundamental physics under conditions that cannot be replicated anywhere else. The extreme magnetic fields generated in this environment are millions of times stronger than anything achievable in terrestrial experiments, allowing astronomers to study how matter behaves in regimes where magnetic forces can compete with or even dominate over gravitational effects. Future observations of the galactic center promise to reveal even more details about these complex interactions. The next generation of telescopes, both ground-based and space-based, will have the sensitivity and resolution needed to track individual stars as they orbit Sagittarius A star with unprecedented precision. These observations will provide new tests of general relativity, reveal details about the black hole's spin and magnetic field structure, and possibly detect the gravitational wave signals produced when stellar mass objects spiral into the central black hole. The James Webb Space Telescope, with its incredible sensitivity to infrared light, has already begun providing new insights into the stellar population near Sagittarius A star. Its ability to peer through the dust that obscures visible light from the galactic center is revealing previously hidden details about star formation and stellar evolution in this extreme environment. Even more exciting are the prospects for future gravitational wave astronomy. While current detectors like LIGO are primarily sensitive to mergers between stellar mass black holes, future space-based interferometers will be able to detect the gravitational waves produced when stars or other compact objects spiral into supermassive black holes like Sagittarius A star. These observations will provide an entirely new window into the physics of strong gravitational fields and the behavior of matter in the immediate vicinity of black holes. As we continue to study this remarkable stellar community that calls the galactic center home, we're gradually piecing together a more complete picture of how supermassive black holes shape their environments and influence the evolution of matter and energy on galactic scales. Each new observation adds another thread to the tapestry of understanding that connects the smallest scales of particle physics to the largest structures in the observable universe. This expanding tapestry of understanding leads us to consider how Sagittarius A star fits into the broader cosmic picture, how our galactic giant compares to its counterparts in other galaxies, and what these comparisons reveal about the fundamental processes that shape the universe on the largest scales. When we turn our telescopes beyond the boundaries of our own galaxy, we discover that supermassive black holes are not rare cosmic oddities, but rather standard equipment for virtually every large galaxy in the observable universe. The relationship between galaxies and their central black holes turns out to be remarkably systematic. There's a tight correlation between the mass of a galaxy's central supermassive black hole and various properties of the galaxy itself, particularly the mass of its central bulge of stars. This relationship, known as the M-sigma relation after the mathematical symbols used to describe it, suggests that galaxies and their central black holes grow together through intimate feedback processes that operate over billions of years. Sagittarius A star, with its 4 million solar masses, fits comfortably within this cosmic pattern. Our galaxy's central bulge contains roughly 10 billion solar masses of stars, giving a black hole to bulge mass ratio that matches what astronomers observe in other spiral galaxies. This consistency across the universe implies that the processes responsible for black hole and galaxy coevolution are fundamental features of cosmic structure formation, operating in similar ways regardless of local conditions. But while the overall relationship between black holes and galaxies appears universal, individual systems show fascinating variations that reveal the complex history of galactic evolution. Some galaxies contain black holes that are unusually massive compared to their stellar content, suggesting episodes of rapid black hole growth during their past. Others have central black holes that seem undersized, possibly indicating that feedback processes halted their growth before they could reach their full potential. These variations provide clues about the different evolutionary pathways that galaxies can follow. Galaxies that have experienced major mergers tend to have more massive central black holes, reflecting the coalescence of multiple smaller black holes during the merger process. Galaxies that have evolved more quietly, growing primarily through the gradual accumulation of gas and smaller satellites, tend to have black holes that follow the standard scaling relations more closely. The study of active galactic nuclei, where supermassive black holes are currently feeding voraciously and shining as brilliant quasars, provides insights into what Sagittarius A star might have looked like during its own active phases. These distant objects, some so far away that we're seeing them as they were when the universe was less than 1 billion years old, show us supermassive black holes in the process of rapid growth, accreting matter at rates thousands of times higher than what we observe around our galactic center today. The energy output from these active galactic nuclei is truly staggering. A single feeding supermassive black hole can outshine the combined light of hundreds of billions of stars, making it visible across billions of light years of expanding space. The radiation pressure from this intense emission can drive powerful winds that sweep through the host galaxy, heating and dispersing gas clouds, and regulating the rate of star formation throughout the entire system. This feedback mechanism appears to be crucial for understanding why galaxies have the properties we observe today. Without the regulating influence of supermassive black holes, computer simulations suggest that galaxies would form stars much more rapidly and efficiently, quickly converting all their available gas into stellar form. The result would be a universe filled with galaxies that are much redder, older, and more metal-rich than what we actually observe. The relatively quiet state of Sagittarius A star today reflects our galaxy's mature phase of evolution. The Milky Way has already experienced most of its major growth episodes, including the accretion of smaller satellite galaxies and the associated merger of their central black holes. Our galaxy now exists in a relatively stable configuration, with star formation proceeding at a leisurely pace and the central black hole feeding only sporadically on the sparse material that wanders within its gravitational reach. But this quiescent state doesn't mean that dramatic changes aren't in store for our galactic future. In approximately 4.5 billion years, the Milky Way is destined to collide with our nearest large galactic neighbor, the Andromeda Galaxy. This cosmic collision will trigger the most significant transformation our galaxy has experienced since its initial formation, reshaping its structure and reawakening its central black hole. The merger with Andromeda will bring together two supermassive black holes, with Sagittarius A star eventually spiraling together with Andromeda's central black hole in a cosmic dance that will culminate in their coalescence into an even more massive object. This process will release enormous amounts of energy in the form of gravitational waves, creating ripples in space-time that will propagate across the universe at the speed of light. The gravitational wave signal from this future merger will be detectable by space-based interferometers, providing astronomers billions of years from now with detailed information about the masses, spins, and orbital characteristics of the merging black holes. These observations will offer unprecedented insights into the final moments before two cosmic giants become one, testing our understanding of general relativity in the strongest possible gravitational fields. The merger will also trigger a spectacular burst of star formation as gas clouds throughout both galaxies are compressed and heated by the gravitational upheaval. The combined system, sometimes nicknamed Milkomeda by astronomers, will likely evolve into a large elliptical galaxy with a central supermassive black hole containing roughly 10 million solar masses, more than twice the current mass of Sagittarius A star. This future transformation illustrates how supermassive black holes serve as fossil records of galactic evolution, preserving information about the merger history and growth processes that shaped their host systems. By studying the properties of supermassive black holes in galaxies of different types and ages, astronomers can trace the evolutionary pathways that lead from the simple initial conditions of the early universe to the complex galactic ecosystem we observe today. The role of supermassive black holes in cosmic evolution extends beyond individual galaxies to the largest scales of cosmic structure. The feedback processes triggered by black hole activity can affect the properties of entire galaxy clusters, heating the intergalactic medium and preventing excessive cooling and star formation in the most massive systems. This regulation helps maintain the diversity of galaxy types we observe and prevents the universe from becoming dominated by a few extremely massive galaxies. Recent advances in computational astrophysics have made it possible to simulate the co-evolution of galaxies and their central black holes with unprecedented detail and realism. These simulations track the complex interplay between gravity, gas dynamics, star formation, stellar feedback, and black hole accretion across cosmic time, revealing how all these processes work together to create the structured universe we inhabit. The results of these simulations underscore the central importance of supermassive black holes in cosmic evolution. Galaxies that form in simulated universes without black hole feedback evolve very differently from those that include these regulatory mechanisms, producing stellar populations and galaxy properties that don't match observations of the real universe. This computational evidence strongly supports the idea that supermassive black holes like Sagittarius A* are not just passive occupants of galactic centers, but active participants in shaping the cosmos. The study of supermassive black holes has also revealed deep connections between seemingly disparate areas of physics. The behavior of matter in the extreme gravitational fields near black holes provides natural laboratories for testing theories of quantum gravity, while the large-scale influence of black hole feedback connects to cosmological processes that operate across billions of light-years. These connections highlight one of the most beautiful aspects of modern astrophysics: the way that understanding extreme objects like Sagittarius A* illuminates fundamental principles that apply throughout the universe. The same physical laws that govern the behavior of matter spiraling into our galactic black hole also determine the formation of the first stars, the evolution of galaxy clusters, and the ultimate fate of cosmic structure in the far future. As our observational capabilities continue to improve, we can expect even more detailed insights into the physics of supermassive black holes and their role in cosmic evolution. The Event Horizon Telescope is already planning observations with higher resolution and sensitivity, potentially allowing us to study the immediate vicinity of Sagittarius A* with unprecedented detail. Future gravitational wave observatories will open entirely new windows into black hole physics, detecting the coalescence of supermassive black holes throughout the observable universe, and providing information about their properties that cannot be obtained through electromagnetic observations alone. These multi-messenger observations, combining gravitational waves with traditional astronomy, will revolutionize our understanding of how these cosmic giants form, grow, and influence their surroundings. The next generation of space telescopes will also contribute to this expanding understanding, with instruments capable of detecting and studying supermassive black holes in the most distant galaxies. When the universe was young and these objects were first forming, these observations will provide crucial insights into the early phases of black hole and galaxy coevolution, filling in missing pieces of the cosmic story. Perhaps most remarkably, the study of Sagittarius A* and its cosmic relatives continues to reveal new connections between the smallest and largest scales of physical reality. From the quantum mechanical processes that govern Hawking radiation to the cosmological dynamics that shape galaxy clusters, supermassive black holes serve as bridges between different realms of physics, connecting our understanding of fundamental particles to the evolution of cosmic structure itself. In this grand cosmic perspective, Sagittarius A* emerges not just as an exotic object worthy of study in its own right, but as a key to understanding some of the deepest questions in physics and astronomy. Its gentle gravitational influence has helped create the stable galactic environment that allowed our solar system to form and evolve, while its more dramatic past phases contributed to shaping the overall structure and chemical composition of our galaxy. This profound connection between our cosmic understanding and our place in the universe brings us to one of the most remarkable aspects of studying Sagittarius A*, the way it transforms our perspective on existence itself. When we gaze toward the galactic center, we're not just looking at a distant astronomical object. We're contemplating the gravitational heart that has quietly orchestrated the cosmic symphony in which our own story unfolds, the invisible conductor that has helped maintain the delicate conditions necessary for life to emerge and flourish in our corner of the galaxy. The realization that we exist within the gravitational embrace of a supermassive black hole might seem unsettling at first, like discovering that your peaceful neighborhood sits next to a sleeping volcano. But Sagittarius A star is not a threat to our existence. Instead, it's been our cosmic guardian for billions of years, its massive presence providing the gravitational stability that allows our galaxy to maintain its elegant spiral structure and our solar system to follow its predictable orbit through the galactic disk. Consider the extraordinary chain of circumstances that had to align for us to exist at this moment, contemplating our galactic center from this small rocky planet. Our solar system formed in just the right location within the galaxy, far enough from the intense radiation environment of the galactic center to avoid sterilization, but close enough to benefit from the heavy elements forged in previous generations of stars. The timing of our formation coincided with a period when the galaxy had reached chemical maturity, but was no longer experiencing the violent disruptions of its youth. Even our current position in the galaxy reflects this cosmic choreography. As our solar system orbits the galactic center every 230 million years or so, we pass through different galactic environments, sometimes venturing closer to active star-forming regions, sometimes drifting into the quieter spaces between spiral arms. These galactic seasons have likely influenced the development of life on Earth in subtle but important ways, affecting the rate of cosmic ray exposure, the frequency of nearby supernovae, and the availability of heavy elements for planet formation. The gentle influence of Sagittarius A star extends even to the fundamental constants of physics that make our existence possible. The mass of our galactic black hole, the structure of our galaxy, and our position within it all had to fall within relatively narrow ranges for complex chemistry and biological evolution to proceed. If Sagittarius A star were much more massive, the increased gravitational forces might have disrupted the formation of stable planetary systems. If it were much less massive, our galaxy might lack the structural organization necessary to maintain a stable galactic environment over billions of years. This cosmic fine-tuning extends beyond our local galactic neighborhood to encompass the fundamental properties of the universe itself. The strength of gravity, the mass of fundamental particles, and the rate of cosmic expansion all appear to be calibrated within narrow ranges that permit the formation of stars, planets, and ultimately life. While scientists continue to debate whether this apparent fine-tuning reflects deeper physical principles or simply the selection effects of our own existence, it's undeniable that we inhabit a universe remarkably well-suited to producing complexity and consciousness. The study of Sagittarius A star also illuminates the deep time scales on which cosmic evolution operates. While human civilization has existed for only a few thousand years, and our species for only a few 100,000, our galactic black hole has been shaping the evolution of matter and energy for billions of years. The atoms in our bodies were forged in stellar furnaces that operated under the gravitational influence of Sagittarius A star, mixed and dispersed by stellar winds and supernova explosions that occurred within our galaxy's evolved structure. This perspective on deep time can be both humbling and comforting. Humbling, because it reminds us how brief our individual and collective existence is compared to the vast spans of cosmic history. But comforting, because it reveals that we are part of an ongoing story that began long before we arrived and will continue long after we're gone. We are not separate from the universe looking in, but rather the universe becoming aware of itself through conscious observation and contemplation. The philosophical implications of studying black holes extend beyond questions of cosmic evolution to touch on some of the deepest mysteries of existence. The event horizon of Sagittarius A star represents a boundary not just in space, but in our understanding of reality itself. Beyond that threshold, the familiar concepts of cause and effect, space and time, and even the flow of information break down or become fundamentally altered. This confrontation with the limits of knowledge has always been one of the most profound aspects of studying black holes. They force us to acknowledge that there are regions of reality that may be forever beyond our direct observation and understanding. Yet rather than discouraging scientific inquiry, these limitations seem to inspire even greater efforts to push the boundaries of what we can know and understand about the universe. The information paradox that we discussed earlier represents more than just a technical problem in theoretical physics. It touches on fundamental questions about the nature of reality, the permanence of information, and the ultimate fate of consciousness in a universe dominated by black holes. If information truly can be lost when it falls into a black hole, it suggests that the universe is fundamentally lossy, that details about the past can be erased irretrievably. But if information is preserved in subtle quantum mechanical ways, it implies a universe where every detail of history is somehow encoded in the structure of space-time itself. These questions become even more poignant when we consider the ultimate fate of consciousness in the universe. As stars age and die, and galaxies drift apart due to cosmic expansion, supermassive black holes like Sagittarius A star will eventually become the longest-lived objects in the cosmos. During the black hole era of the far future, these cosmic giants will slowly evaporate through Hawking radiation over timescales that dwarf the current age of the universe by factors too large to comprehend. Yet, even in this seemingly desolate future, some physicists have speculated that black holes might serve as engines for computation and consciousness, processing information at rates determined by their temperature and size. The Hawking radiation from evaporating black holes might encode complex patterns that could, in principle, support forms of information processing and perhaps even consciousness radically different from anything we experience today. These speculative visions of the far future remind us that studying Sagittarius A star is not just about understanding our cosmic past, but about contemplating the deepest questions of existence itself. What does it mean to be conscious in a universe where most of space and time will be dominated by black holes? How might intelligence and awareness persist or transform in environments we can barely imagine? The remarkable thing about these questions is that they arise naturally from careful scientific observation and analysis. We didn't set out to study black holes in order to probe the nature of consciousness or the ultimate fate of information. These profound philosophical implications emerged as unexpected consequences of trying to understand the behavior of matter and energy in extreme gravitational environments. This pattern, where scientific investigation reveals deeper layers of meaning and connection, has characterized much of our exploration of Sagittarius A star. What began as an attempt to understand strange radio emissions from the galactic center has evolved into a comprehensive investigation of gravity, space, time, and the fundamental nature of reality itself. The process of discovery itself has been as remarkable as the discoveries themselves. The decades-long effort to image Sagittarius A star required unprecedented levels of international cooperation, bringing together scientists from around the world to work toward a common goal. The technical challenges were so demanding that they drove innovations in telescope technology, data processing, and computational techniques that have applications far beyond astronomy. This collaborative aspect of modern astrophysics reflects something profound about human nature and our relationship with the cosmos. Despite our differences in culture, language, and political systems, humans everywhere seem to share a fundamental curiosity about the universe and our place within it. The study of Sagittarius A star has brought together researchers from every continent, united by their desire to understand something that belongs to all of humanity equally. The images and data from the Event Horizon Telescope don't belong to any single nation or institution. They are part of humanity's collective heritage, expanding our understanding of the cosmos in ways that transcend political boundaries and cultural divisions. In a world often divided by conflict and competition, the study of our galactic center reminds us of our shared identity as cosmic beings, inhabitants of a small planet, orbiting an ordinary star in the outer suburbs of one galaxy among billions. Looking toward the future, the study of Sagittarius A star promises to remain at the forefront of scientific discovery for generations to come. Each new technological advance opens up possibilities for more detailed observations and deeper understanding. The gravitational wave astronomy revolution has only just begun, and future detectors will be sensitive enough to observe the coalescence of supermassive black holes throughout the observable universe. Advanced space telescopes will probe the galactic center with unprecedented resolution and sensitivity, potentially revealing details about the immediate vicinity of the event horizon that we can barely imagine today. Quantum technologies might eventually allow us to study the subtle quantum mechanical effects that occur near black holes. testing our understanding of physics in regimes where quantum mechanics and general relativity intersect. But perhaps the most exciting prospect is the possibility of entirely new types of observations and measurements that we haven't yet conceived. The history of astronomy is filled with unexpected discoveries that opened up new ways of studying the universe. Radio astronomy, X-ray astronomy, gravitational wave astronomy, and neutrino astronomy all revealed phenomena that were completely unknown when they were first developed. The continuing study of Sagittarius A star will likely surprise us with discoveries we cannot currently anticipate, revealing new aspects of black hole physics and cosmic evolution that will reshape our understanding of the universe once again. These future discoveries will build upon the foundation of knowledge we've established through decades of patient observation and analysis, adding new chapters to humanity's ongoing conversation with the cosmos. As we drift toward the end of our gentle journey through the cosmic depths surrounding Sagittarius A star, it's worth pausing to consider how this invisible giant continues to weave its influence through every aspect of our existence, even in ways we're only beginning to appreciate. The gravitational waves that ripple outward from our galactic center, too subtle for us to detect directly but nonetheless real, carry information about the deep structure of space-time itself, connecting us to the fundamental rhythms of the universe in ways that transcend our ordinary experience of space and time. These cosmic vibrations remind us that we live in a universe where everything is connected, where the motion of matter around a black hole 26,000 light-years away can influence the delicate measurements scientists make in laboratories on Earth. The precision required to detect gravitational waves from distant black hole mergers is so extraordinary that it pushes the boundaries of what's technically possible, requiring instruments sensitive enough to measure changes in distance smaller than 1,000th of the width of a proton. This remarkable sensitivity has opened up an entirely new way of experiencing the cosmos, one that relies not on light or any other form of electromagnetic radiation, but on the fundamental fabric of space-time itself. When two black holes spiral together and merge somewhere in the distant universe, they create ripples that travel outward at the speed of light, carrying with them information about the masses, spins, and orbital characteristics of the merging objects. These gravitational messages reach Earth after journeys that may have lasted billions of years, arriving as whispers so faint that they require the most sophisticated detection systems ever built to capture them. Yet in those whispers, we can hear the authentic voice of gravity itself, speaking to us across cosmic distances about events so violent and energetic that they briefly outshine all the stars in the observable universe combined. The prospect of detecting gravitational waves from the eventual merger of Sagittarius A star with another supermassive black hole opens up tantalizing possibilities for understanding our galactic center in ways that electromagnetic observations alone could never provide. Gravitational waves carry information about the interior structure of black holes, their rotation rates, and the detailed dynamics of their merger process that remains hidden from conventional telescopes. When our galaxy eventually collides with Andromeda in several billion years, the resulting gravitational wave signal will provide a front-row seat to one of the most spectacular events in cosmic history. Future astronomers, whether human or whatever form of consciousness emerges to replace us, will be able to track the spiral dance of two supermassive black holes with exquisite precision, measuring how the fabric of space-time itself responds to these ultimate expressions of gravitational power. But even in its current quiet state, Sagittarius A star continues to teach us about the nature of reality in ways that extend far beyond astrophysics. The study of black holes has forced physicists to confront some of the deepest questions about the relationship between information and physical reality, leading to insights that may eventually revolutionize our understanding of computation, consciousness, and the fundamental nature of existence itself. The holographic principle that emerged from black hole physics suggests that all the information contained in a volume of space might be encoded on its boundary, much like the way a hologram stores a three-dimensional image in a two-dimensional surface. If this principle applies universally, it would mean that our entire three-dimensional reality might be a kind of projection from information stored on a distant two-dimensional boundary, These ideas blur the traditional distinctions between physics and information theory, suggesting deep connections between the behavior of matter and energy and the processing and storage of information. Some physicists have speculated that the universe itself might be understood as a vast computational system, with black holes serving as natural information processors operating according to principles we're only beginning to understand. The implications of these ideas extend to questions about the nature of consciousness and its relationship to physical reality. If information processing is fundamental to the structure of the universe, and if consciousness emerges from certain types of information processing, then perhaps the study of black holes can illuminate the deepest questions about awareness, experience, and the nature of mind itself. These philosophical ramifications remind us that our journey to understand Sagittarius A star is really a journey to understand ourselves and our place in the cosmic order. Every discovery about black holes reveals something new about the universe we inhabit, but it also reveals something about the remarkable capacity of conscious beings to comprehend and appreciate the elegant complexity of nature. The fact that creatures evolved on a small planet can use their intelligence to probe the structure of space-time around objects as exotic as black holes speaks to something profound about the relationship between mind and universe. We are not separate from the cosmos we study, but rather expressions of its capacity for self-awareness and understanding. This perspective transforms our relationship with Sagittarius A star from mere scientific curiosity to something approaching reverence. Here is an object so extreme that it challenges our understanding of space and time, yet it has played an essential role in creating the stable galactic environment that allowed our planet and our species to emerge. It represents both the ultimate expression of gravitational power and the gentle guardian that has watched over our cosmic neighborhood for billions of years. The light that allows us to study our galactic center began its journey long before Earth had formed its oceans or developed its first signs of life. Photons that left the vicinity of Sagittarius A star when the universe was young and chaotic have traveled across expanding space to arrive at our telescopes today, carrying with them information about cosmic conditions that existed billions of years ago. In that ancient light, we can read the history of our galaxy's evolution, the story of how structure emerged from simplicity, and the ongoing dance between creation and destruction that continues to shape the cosmos around us. Each photon is a messenger from the deep past, a tiny ambassador carrying news of events that occurred when the universe was fundamentally different from what we observe today. The patient accumulation of these cosmic messages over decades of observation has gradually revealed the nature of our galactic center, transforming it from a mysterious radio source to a well-characterized supermassive black hole, whose properties we can measure with remarkable precision. This transformation represents one of the great triumphs of modern astronomy, demonstrating how human ingenuity and persistence can unlock the secrets of even the most exotic objects in the universe. Yet, for all our growing understanding of Sagittarius A star, it retains an essential mystery that may never be fully resolved. The event horizon represents a fundamental boundary, not just in space, but in knowledge itself. Beyond that threshold, the familiar concepts of space and time break down, and information disappears from our observable universe in ways that challenge our deepest assumptions about the nature of reality. This confrontation with the limits of knowledge is perhaps one of the most valuable aspects of studying black holes. They remind us that the universe is under no obligation to conform to our expectations or to reveal all its secrets to scientific investigation. There are regions of reality that may forever remain beyond our direct observation, mysteries that may never be fully solved. Rather than being frustrating, this recognition can be liberating. It reminds us that wonder and mystery are not obstacles to understanding, but essential features of a universe rich enough to support consciousness and curiosity. The fact that we can push the boundaries of knowledge so far, even while acknowledging their ultimate limits, is itself a remarkable achievement. As we settle into sleep, drifting gently away from our exploration of the cosmic giant at our galaxy's heart, we can rest in the knowledge that Sagittarius A star continues its ancient work of maintaining the gravitational architecture that makes our existence possible. Its massive presence provides stability and structure to our galactic home, ensuring that the delicate conditions necessary for life can persist across the vast timescales of cosmic evolution. The invisible threads of gravity that connect us to our galactic center span 26,000 light-years of space, yet they bind us to the cosmic story in ways that transcend distance and time. We are not isolated observers looking out at an alien universe, but participants in an ongoing cosmic drama that began billions of years ago and will continue long after our individual stories have ended. In the gentle darkness of the night sky, Sagittarius A star remains hidden from view, its presence known only through the subtle gravitational choreography it conducts among the stars around it. Yet in that darkness lies one of the most profound reminders of our cosmic heritage, a monument to the creative power of gravity and the elegant complexity of the universe we call home. The story of our journey to understand this cosmic giant reflects something beautiful about human nature and our relationship with the cosmos. Despite our brief existence compared to cosmic timescales, we have managed to probe some of the deepest mysteries of space and time, revealing connections and patterns that span from the smallest quantum scales to the largest structures in the observable universe. In reaching toward understanding Sagittarius A star, we reach toward understanding ourselves and our place in the vast, gentle darkness that surrounds us all.